I'm going to discuss is about the design of combined footing. So, uh, first of all, I would like to introduce about the combined footing. And as we know, the function of a footing is to transfer the load from a superstructure to a soil, to the underlying soil. In generally, it is called as foundation, and footing is a part of it. And the object of providing the footing to a structure is to distribute the load to the soil in such a way that the maximum pressure on the soil does not exceed its permissible bearing value, and at the same time, it does not even exceed the permissible limits of settlement also. And the choice of footing depends upon the depth at which the bearing strata lies and the soil conditions and the type of superstructure that we are about to construct. And now we can see that combined footing are provided only when there is an absolutely necessary under these conditions, when two columns are very close and are overlapping of adjacent. Is everybody audible? Am I audible to you?
Yes, yes, perfectly audible.
Okay. When two columns are very close together, or they are overlapping of the adjacent isolated footing, we saw that whenever we used to design the footings, some of the footings used to overlap, so we can provide combined footing. And even when the bearing capacity of the soil is low, then also we can provide combined footing. And proximity of a building or a line is adjacent to a sewer or else adjacent building column, or else there is a property line which obstructs us from providing an isolated footing, then also we can provide combined footing. And in this image we can see that P1 is the load and P2 is the uh, load of another column, and x is the distance from the P1 to the point of center of gravity of the footing. In the next slides, we are going to learn about how in rectangular footing, but rectangularly combined footing bends. So we can see that in longitudinal bending, the T donates the what we call it as bending. So in longitudinal way, and footing is going to bend in this way, where P1 is one column and P2 is another column, and A1 and A and B are the projections of an combined footing, and in transverse way it is going to bend like this. So generally this behaves as an cantilever, and this is can be imagined as a beam, and this can be columns. In such a way we can imagine so that we can understand it better. And let us know the design procedure of a slab type combined footing. And in this there is an step one, that is we should find out the footing slab dimensions, that is calculation of the loads and the area of the footing sizes and area to be provided, and the projections of the footing. And as we see in this image, we can see that PA is the load on the A column and PB is the load on the B column, and D is the okay. Uh, as DF is the effective depth, and x dash is the distance from the PA to the point of centroid. And 1 minute. Okay. Uh, okay. So first we can observe that PA and PB are the axial load on the columns, and yeah, we should provide the area of the column in such a way that PA plus PB plus P dash by Q, which is Q is an bearing capacity of the soil, and the area to be provided is in the form of L into B. And uh, we should also calculate the distance, that is x dash that is CG from the columns on the loads, so that we can the actual rule of designing a combined footing is that the CG of the footing should coincide with the CG of the loads. So these formulas are provided, that is P1 plus x dash is equal to L by 2, and P dash is equal to PA x1 plus PB x2 divided by PA plus PB. And Next step is net upward pressure intensity on the footing. We should be calculating. And uh, fourth one is calculation of bending moment and shear force with the diagrams, and calculations of depth of the footing, and check for punching shear or two-way shear, and check for the depth, and design of longitudinal reinforcement and reinforcement for hogging in BM bending moment, and hogging bending moment and sagging bending moment, and check for one-way shear, and design of transverse reinforcement for column A and column B and the remaining portions. Let us see. Uh, this is the problem. So suppose if you want to design an combined footing, say of two columns A and B carrying loads 500 kilonewton and 700 kilonewton, and the column A of size 300 into 300 mm and column B of size 400 into 400 mm, and the center to center distance between these columns is around 3.4 meter, let us assume, and the safe bearing of capacity of the soil is given as 150 kilonewton per meter square, and we use M20 concrete and FU 415 grade of steel. So we write down the given data in such a manner that we can understand. Okay, and next is we should, as we saw in the steps, step one is to find the size of the footing or the footing slabs dimensions. So first we can calculate the calculations of loads, that is PA plus PB, that is 500 kilonewton plus 700 kilonewton, that is 1200 kilonewton, and we should increase the load by 10% as in self weight of the footing, so that that comes out to be 120 kilonewton, and the summation of is 1320 kilonewton, and we have to find the area of the footing, that is P 1220 kilonewton divided by SPC that we have taken. So we get around 8.8 meter square of area that is required for the footing to transfer the load. And next is footing size and the area of the footing to be provided. So we should fix the breadth of the footing, that is that I have taken as 2 meter, and as we know the area is equal to L into B, we should calculate the length of the column that we should require. So it comes out to be 4.5 meter, and we should check the area to be provided and the area required. So 9 meter square is the area of the footing that I have taken, and 8.8 meter was required. And let us calculate the projections of the footing. So in projections of footing, we should calculate the P1 and P2 should be required in such a way that CG, that is center of gravity of a footing, should be coincide with the center of gravity of the column, and that is CG of the footing is equal to CG of the column. And we should find the X dash, that is this distance from the columns by the given formula. So we can see that L by 2 is almost 2.25, and L by 2 is L by 2.25. And again, this is a column A, this is column B. Column A is of 300 into 300 mm size, and column B is of 400 into 400 mm size. And respectively, we should calculate the A1, A2, B1, B2, and this is what P1 and P2, and the total length is around 4.5 meter, and the center to center distance is given in the formula, our problem itself, that is 3.4 meter. So the next is calculation, that is this is P1, this is P2. We should calculate by using these formulas, that is P1 plus X dash is equal to L by 2. That is the CG of the footing is believed to be lying in the center of the entire column. So L by 2 is the center of the footing, and using these two formulas we can work out that P1 is okay, X dash is 1.983, that is 2 meter. So this is 2 meter, and next is P1 plus X dash. So we can find the P1 by substituting the formulas. So this is the this is 0.25 meter as we see here, and P2 is 0.85, that is worked out with the formula, that is P1 plus L plus P2, that is P1, this is L, this is P2. So we know P1 and L and L also. So we can find the P2 to be 0.85. So next is step 3. that is, we should find the net upward pressure intensity of the footing, and that is found out in the formula Q is equal to total column load divided by area provided. So we can do this, and this should be less than the SPC of the soil. So hence safe it is, that is 133.34 kilonewton per meter square, which is less than 150 kilonewton, so it is safe. And the next is, we should calculate the bending moment and shear force with the diagrams. So we are getting P2 to be 500 kilonewton and PB is 700 kilonewton. So W is equal to that is 266.68 kilonewton per meter square, which is uh, 2 times the 133, because the width that we have considered is 2, so we should multiply the net upward pressure with the 2 so that we can take the load, and similarly we can calculate the shear force and bending moment. So we should work out this point of contraflexure, that is where the shear force is 0, and that is where the maximum bending moment lies for a column. So for the slab, so that is that comes out to be 343.78 kilonewton meter, and end also we should calculate using formulas. So here we can see that the pressure W per length is that is what I told you, to multiply the net upward pressure by 2 to get the W. And yeah, this is calculation for shear force. I think we can skip this part, because here we can see that how to calculate the point of contraflexure, that is x, that is the distance from the column A, so that we can calculate the bending moment here also. And similarly we can work out the formulas and find the maximum bending moment to be almost 343.73 kilonewton meter. And next is calculation for the depth of the footing, that is the effective depth we should find out using this formula, that is df is equal to root of mu divided by 0.138 fck into p. So mu we should calculate by 1.5 times multiplication of whatever the maximum that we have got. That depth comes out to be around 305.62, say around 310 millimeter. That is the depth of effective depth that we require for a footing. And the step 4 is check for the punching shear or two-way shear. So in this we should calculate the A dash, that is this one, and B dash. So we can see that let us check the depth for a punching shear, for which the critical section or a plane lies around depth of effective depth divided by 2, that is 310 divided by 2, which is 155. For a column B, we should check for the bigger column with a bigger load, so that we can know the punching shear. So that comes out to be around 710 and 710 mm for A dash and B dash. So punching shear should be factored using 1.5. So this is the load of axial load we are getting on the column B, minus the Q, that is upward net upward pressure, into A dash, A naught into B naught. If we do it, we can get the maximum punching shear, that is 949.17 kilonewton. So we should check using this formula for nominal shear stress, that is tau V, we are getting around 1.078 Newton per mm square, and permissible shear stress, that is K is equal K into tau C, which is the shear stress offered by concrete. Using this formula 0.25 into root of FCK, by referring to the IS code 456/2000 using clause 31.6.3.1, and the K factor is 1 for the depth of footing more than 300 mm as per the IS code 456/2000 clause number 40.2.1.1. So our shear force that is acting on the footing is tau V, which is less than the K tau C. That means the concrete has enough shear strength to provide um, against the failure of the footing on punching shear. So hence it is safe. If tau v that is worked out is greater than the tau c, then we should provide the um, shear reinforcement with respect to this formula, that is just reverse of this formula. That means df went here and tau v just came here. So this is how we should provide check for the depth for a column or a footing which is having the shear force. Next is step 7, that is design of bending tension for in longitudinal direction and the design of longitudinal reinforcement. For we saw that the maximum bending moment was around 343.73 kilonewton meter. So it is multiplied by 1.5 to get the factored maximum ultimate bending moment that will be acting on the footing. So um, even this one, that is for under reinforcer, we should always design the building in the under reinforcer section so that the building gives enough warning before even failure or collapse. So for calculating the AST required, we should have work out with this formula, which is from the reference of IS 456 2000 annexure G 1.1, that is B. In we suppose if we open the IS 456 2000, we can see that this formula is in the annexure G of the IS 456. So after substituting the value of mu, which is for 505.6 into 10 to the power of 6 Newton millimeter, and all the values, we can work out with the AST. So the AST comes out to be 5687.55 millimeter square. So we should also calculate the spacings, that comes out to be 770 mm, which is less than the 3D. That is okay. 3D is 3 into 3. 310, that is 930 mm, so it is less than the 3D, so we should provide 70 mm, that is 16 mm bars at 70 mm center to center spacing on the top face of the footing, and AST provided can be calculated here. And we should also calculate the AST that is required for the sagging bending moment. For example, for a bending moment at A, which is 8.33 kilonewton per meter, we should multiply with 1.5, and with the same formula we can work out the AST, that is 112.10 millimeter square. So which is very less. So we should provide a minimum AST which is 0.12 times the gross cross section area. So we provide the 888 mm square rather than this, because minimum AST has to be provided along the cross section. So the AST should be, we can use the 12 mm bars at 250 mm center to center at the bottom face, and we should also provide the reinforcement along the longitudinal bars in the B column, under the B column. So there we have the bending moment as 96.33 kilonewton meter. So we should multiply it by 1.5. Then we get to the 144. We should substitute the same in this formula, and we should work out the AST. AST comes out to be 1352.12 millimeter square, which is greater than the minimum AST. So we should provide the AST according to this. So we can use the 12 mm bars at 150 mm center to center at the bottom face of the footing, and this works to be okay. This is AST provided, which is to be greater than the AST required. That's all. And we should check for the one-way shear. So for checking the one-way shear, critical section is taken as for a distance of effective depth, that is df, from the column B face, that is longer column. So d by 2 is around 400 m by 2, that is the dimension of the column is 400 mm, that is taken as d by 2. This is the length, and the df, that is 310 mm. So we should add both of these, and both of this comes out to be 510 mm, which is where our one-way shear actually acts. So we can multiply the uh, one-way shear with 1.5 and find out the uh, actual amount of shear force, that is 136 kilonewton per meter, which acts on the footing. So the tau v is equal to vu by bd, which is given by IS 456 2000 clause 40.1, and we should divide it by b into effective depth. Then we can find the tau v, that is 0.22 newton per millimeter square, and considering the support, the sagging bending moment of the area of cross section. Okay, and consider a dash cross section. With there, we should provide an AST is provided as 904.72 millimeter square, and this is calculated by the formula PT is equal to 100 into AST provided divided by B into DF, and that is effective depth. So we can multiply it, and percentage of steel that comes out to be 0.15 percentage. So we should calculate the tau c according to it, by using the by referring to IS 456 2000 table number 12. We can find the what is the shear force that is offered, shear strength that is offered by the concrete. The tau c for in concrete with FCK value, that is M20 concrete with the percentage of steel as 0.15%. So the tau c comes out to be 0.28 Newton per mm square, and permissible shear stress, that is K tau c, is 1 into 0.28. So we can observe that the shear strength offered by the concrete is more than the actual nominal shear stress that is acting on the footing. So hence it is safe. So we do not require to provide any shear reinforcement, but we should provide the minimum shear reinforcement. Okay, and even in the BB cross section, BB dash, we can we know that we have provided in AST, that is area of steel, that is 507.86 millimeter square. So we can work out with the formula, and we can find that the case tau c, that is shear strength offered by the concrete, is more than the nominal shear stress that is acting on the footing. So we do not require to provide shear reinforcement, but we should provide a minimum shear reinforcement as per the IS 456 2000 clause number 26.5.1.6. So there is three conditions to provide a shear reinforcement. One is we should work out the area of shear reinforcement from this formula, and another one is we should provide suppose if you want to provide eight legged vertical shear stirrups of 8 mm dia, then we can provide then we should calculate the area of shear reinforcement, which comes out to be 402.12 millimeter square. We can substitute this in the formula and can find out the spacing, that is that comes out to be 175 mm, and spacing should not be greater than 0.75 into d, which is effective depth. So it is so in three conditions we should pick the whichever is the least of the above three values. That comes out to be 175 mm square of the space for the spacing of the shear reinforcement should be around we should provide 8 mm dia 8 legged vertical shear stirrups at 175 mm center to center in cantilevered position, both A dash and B dash, that is this one, A into A dash and B to B dash. We should provide the shear reinforcement with 175 mm center to center distance, and similarly you can provide okay. And the design for shear reinforcement and transverse reinforcement should be worked out separately. That is, we can see that the reinforcement to be provided in this way, transverse to prevent the transverse bending of the combined footing. So we should first calculate the bending moment, that is queued we should first work out the net upward pressure, that is Q naught dash, that is PA. That is PA is the axial load acting on the column A, and B is the breadth of the footing, that is 2, and 0.92 is worked out in the using this one. This this formula, that is B plus 2 into BD, which is cantilever projection behind the face of the column A. So the maximum bending moment that we are going to maximum net upward pressure that is going to act on the transfer reinforcement is around 271.73 kilonewton per mm square. So using this formula, we should calculate the bending moment and multiply it with factor of safety, that is 1.5. So that comes out to be 147.24 kilonewton meter, and the depth of the footing to be provided, we should check for the depth that we have provided, so that we should revise the column. So for checking the upon checking the depth of the footing, so using this formula, D is equal to root of mu divided by 0.138 fck into B. Depth of footing comes out to be 230 minimum we should provide, but we have already provided 310 mm depth, so it is sufficient. So transverse beam will thus be able to take the load with the same thickness, so we should not be increasing any depth. And we should work out the AST required using this formula that is given in the IS 456 annexure A, annexure G, and the AST comes out to be around 1531 millimeter square. So we can assume to provide 12 mm bars. So the spacing should be worked out, which is almost 70 mm, which is same. And for transfer reinforcement under the column A, we can provide 12 mm bars at 70 mm center to center for a width of 920 mm above the longitudinal bars at the bottom. And for column B, we can separate, we can calculate the AST required separately. That comes out to be around 1742.02 mm square. For we can also use the same 12 mm bars, and the spacing should be around 60 mm, and that should be around 1020 mm from the longitudinal side at the bottom. So at the remaining portions, we should provide the minimum AST, that is 0.12 times the cross section F area, that is 898 mm square. So we can work out the spacing, that is we can provide the 12 mm bars at 250 mm at the bottom of, and should also provide the same reinforcement at the top also. So this is the cross section. This is the sectional elevation of the combined footing that I have designed. That is 250 mm. We can see the projections, and this is the center to center distance between the column, and the 850 mm is the another projection, that is this one. And we can see that 8 mm vertical stirrup, 8-legged vertical stirrups are provided in this phase at a spacing of 175 mm, and in this side we can provide the 8-legged vertical stirrups at 175 mm, that is same. And even we can check the main reinforcement, that is this is the transverse reinforcement, that is dot we are seeing, which is the transverse reinforcement. It is provided at 12 mm bars are provided at 250 mm center to center in the middle portion, and in this projection up to 120 mm from here to here, we can see that it is provided with an spacing of 60 mm. And in this portion, we should provide the 12 mm bars at 70 mm center to center for a width of 920 mm. And in the above, in the top, we should provide 16 mm bars at 70 mm center to center over the top face. And this is the cross section. We can see the 8-legged stirrups, 8-legged 8 mm stirrups, and we can see the bottom bars. This is longitudinal bars, and this is the transverse reinforcement. This is the longitudinal reinforcement. along the sections. And we should provide the meshing of the bottom reinforcement like this. This is the longitudinal reinforcement. So this direction we should provide 12 mm bars at 30 mm center to center in the this portion, and in this portion we should increase the reinforcement, even the longitudinal reinforcement. Here and we can check the transverse reinforcement, which are vertical bars, that is 12 mm bars at provided at 70 mm center to center for a width of 920 mm from here to here, and 200 and for the remaining portion we should provide the minimum reinforcement, and for this portion we can provide the transfer reinforcement to be 12 mm bars at 150 mm center to center, and for the above, that is top mesh, that we can provide the only longitudinal bars, that is 16 mm bars at 70 mm center to center over the top face. So
एक्सीलेंट, बहुत सुंदर, बहुत बढ़िया पवन, जैसा मैंने एक्सपेक्ट किया था आपसे उससे ज़्यादा ही बेटर किया, बहुत सुंदर किया आपने, एक्सीलेंट, मजा आ
yes.
गया। गैस इसको बोलते हैं डेडिकेशन। आप लोगों ने देखा कितना अच्छा इन्होंने प्रेजेंट किया, और सबसे अच्छी चीज़ मुझे लगी इन्होंने एक एक चीज़ की डिटेलिंग्स दिया प्रॉपर। अगर आप लोग समझ रहे थे तो मैंने देखा एकदम मतलब डिटेल में इन्होंने पूरा एक भी स्टेप्स को मिस ही नहीं किया है। चलिए बहुत सुंदर। और इसके बाद जयश्री अभी प्रेजेंट कर रहे हैं गाइस, ठीक है, एंड जयश्री इज गोइंग टू गिव देयर बेस्ट। आप लोग उनको भी देखिए और सीखिए कि देखिए कि इनिशिएटिव कैसे लेना चाहिए। जयश्री के बाद कौन करना चाह रहा है कमेंट करके बता दें। जयश्री यू कैन जस्ट क्लिक ऑन शेयर स्क्रीन कर दो, और शेयर स्क्रीन पर क्लिक करोगे तो तुम्हारा स्क्रीन शेयर हो जाएगा भैया।
ओके सर।
योर इंटायर स्क्रीन कर लेना, हाँ योर इंटायर स्क्रीन। उस एक बॉक्स आएगा, बॉक्स पर क्लिक करोगे तब शेयर वाला बटन आएगा। वेरी गुड दिव्यांशु, इसके बाद आप करिएगा। बहुत बढ़िया पवन, मजा आ गया।
सर हो गया क्या?
यस यस हो गया है। अभी पीपीटी ओपन कर लो पहले, तब देखते हैं। पीपीटी भेज दिया ना जैसे आपने?
हाँ भेज दिया।
वेरी गुड, ठीक।
विजिबल है क्या सर?
एकदम परफेक्ट। फुल स्क्रीन कर लो, अच्छा रहेगा तुम्हारे लिए, मतलब ये इसका पीपीटी का फुल स्क्रीन कर लो। ये कॉर्नर्स पे यहाँ पर होता ना, जहाँ पर ये देखो जूम करने का, नीचे जहाँ लिखा है ENG, नीचे नीचे जहाँ लिखा है ना ENG, इसके ऊपर, हाँ इसी में और आगे, इसी में तीसरा वाला, इसके थोड़ा सा आगे, दो आगे, एक और आगे, हाँ ये वही था। नो 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 ऐसे नहीं, ये जो हाँ ये जो इससे जस्ट पहले जो माइनस का सिंबल है उससे जस्ट पहले वाला है स्लाइड शो। हाँ ये कर लो, तुम्हें अच्छा रहेगा। परफेक्ट। स्क्रॉल करके भी करोगे तो भी चेंज होगा। ये शेयर स्क्रीन वाला जो ऑप्शन है ना, ये पट्टी जो आ रही है, पट्टी खींच के साइड कर दो, बस परफेक्ट।
Good evening everyone. My name is Jayashree. I am here to represent design of Raft Foundation. This PPT includes introduction, design steps and example. First of all, we will see what is Raft Foundation. Raft Foundations, also known as mat foundations, it is continuous slab resting on a soil, extends over the entire footprint. This is the best suitable when basement floor or high-rise structures. Generally, it is where soft soil is present, and we doesn't want to give pile foundations. We don't want to go more deeper in the soil. Then this type of shallow foundations are used. When do we need raft foundation? First is soil has a low bearing capacity. Load transfer to the soil is very high. Deep foundations become uneconomical, that is pile foundations, and there is more number of columns. The total footing area is greater than 50% of the building area. If we provide another foundations like pile foundations or isolated foundations in very large number, and deeper in the ground, then the area of footing is more than the 50% area of the plot area or the building constructed area, then this raft foundation is used. Advantages of this: supports large number of columns, helps in overcome differential settlement, distributes the loads on the wider area, thereby not exceeding allowable bearing capacity. The only shallow foundation to carry heavy loads, resist uplift pressure. Raft foundation is nothing but the slab, which is inverted slab. Then soil pressure is acting on it, hence it is written as resist uplift pressure. There are types of the raft foundations. First one is a flat slab type raft foundation. In the figure, it can be seen there is a slab and slab below, and there are columns. Used when the columns are equally spaced, uniform pressure throughout the slab. Slab has uniform thickness. Usually, raft has uniform thickness. And second type is slab beam type raft foundation. The difference between both is in this first one is columns are not connected by the beams, and second one the columns are connected by the beams, and also there is a cantilever portion of the beams. To avoid excessive distortion of the structure as the result of variation in the load distribution on the raft. In this type of raft foundation, beams are provided with the flat slabs as shown in the figure. The beams add stiffness to the raft foundation. The foundation slabs are reinforced with two or more steel meshes. Two or more steel meshes means there will be mesh below the beam and on the upper edge of the beam. It is written one placed on the lower face of the another at the upper faces of the raft of the foundation. The raft beams are reinforced with strong stirrups and bars placed upper and lower faces. Third one is a pile raft foundation. As shown in the figure, there is a very less compressible strata. Then piles are driven, and then on that pile, a raft slab is taken, and then there is a superstructure. When the soil is so weak that there is an excessive settlement of the raft slab, then slab is called laid on the piles. Load is carried by the raft slab, and settlement is resisted by the piles, as shown in the figure. How to design the slab, raft slab? There are two approaches: rigid foundation approach and flexible foundation approach. In rigid approach, foundation approach, it is presumed that the raft is rigid. Raft is rigid enough to bridge over the non-uniformities of the soil structure. Pressure distribution is considered to be either uniform or varying linearly. Means it has a linear varying pressure. It is considered. It has two types: inverted floor system and combined footing approach. Inflexible approach. In this raft distributes the load in the area immediately surrounding the column depending upon the soil's characteristics. Differential settlements are comparatively larger, but bending moments and shear forces are comparatively low. Flexible plate supported on the elastic foundation, that is Hentley's theory. Which theory is used is written here. Foundation supported on the bed of the uniformly distributed elastic springs with spring constant determined using coefficient of subgrade function reaction. On site, we usually use a rigid approach. How pressure distributed under the raft? The nature of the soil below the raft, the nature of the foundation, that is whether rigid or flexible or soft, rigidity of the superstructure, the quantum loads and their relative magnitude, presence of adjoining foundations, size of the raft, time at which the pressure measurements are taken. These are some images of the raft foundation. In rocky soil, this is the image. On the steep soil, this is the image, and for the soft soil. these images of the contact pressure distribution under the raft. There is a settlement of raft slab. The total settlement under the raft foundation can be considered to be made up of three components. That is, S is equal to SD plus SC and SS, where SD is the immediate or distortion settlement, SC is the consolidation settlement, and SS is the secondary compression settlement. Design of raft, the design of slab beam type of raft slab. The most common approach in medium rise residential commercial buildings. The raft is designed as an inverted slab. The uplift pressure is the loading on the slab, for which bending moment and shear forces are calculated. The raft beams stiffen the raft slabs. Raft beams are designed as inverted floor beams subjected to the uplift pressure. Area of the slab will be the equal to footprints of the building. Cantilever portions are not always necessary. Means these cantilever portions not always necessary, depends on the area required. This is the example I have taken. In this example is design a raft footing for a foundation plan shown. Assume SBC is 150 kilonewton per meter square. There are C1, this is C1, 1, 2, 3, and C2 are 6 numbers of C2. C1 size is 300 into 300, which carries load 800 kilonewton. C2 is 300 by 300, carries 600 kilonewton load. Solution of it: calculation of load columns. Load from the column 1 is 3 into 800, and load from the column C2 6 into 600, it is 3600. Total load on foundation is sum of this, it is 6000 kilonewton. Self weight of the foundation is considered above 10% of this. Then total load is equal to 6600 kilonewton. Area of footing required is A is equal to this load divided by SBC is equal to 44 meters square. Footprint area of the grid is 6.3 and into 6.3. How is 6.3 is considered? Center to center distance is 3 and 3, and then their cantilever, this is center to center distance, and it is 300 by 300 column, hence it is above this level is 150, and beside this is 150, hence it is 6.3, and it is same. It is come 39.69 meters square, which is less than area required. We have total calculated area is 6.3, but we have adapted 7 meter into 7 meter, which is 49 meters square. Since the grid cannot be changed, the extend the raft on the edges on 4 sides as shown in the figure. This is cantilever of 500 mm taken. Net upward pressure P is equal to load of column divided by area provided. Load we have calculated 6000 divided by 49, which we have adapted, which is 122.45 kilonewton per meter square, which is less than SBC. Slab beam type of raft is slab is designed as inverted slab subject to the upward pressure 122.45 kilonewton per meter square. The raft slab has interior panels as well as the cantilever portion. This is the interior panels and this is the cantilever portion. Hence we have designed both interior panel and cantilever portion. First we design cantilever slab. Bending moment M is equal to 1.5 WL square by 2. This is in the IS code. Then M comes 11.25. Interior panel is LY 3 meter, LX is 3 meter. This length LY by LX is equal to 1. Then when LY by LX value is 1, we have a table 26 page number 91 IS 456, which values given for this value 1. Then it comes alpha x is equal to, for this value alpha x is equal to minus 0.032 along longer side, and alpha y is equal to minus 0.032 for negative as well as for positive. This bending moment calculation formula: mx is equal to alpha x wl square by wlx square, and this is the formula for negative. We can use for negative as well as for positive bending moment. Depth required is equal to mu into 0.38 fck bd square, which comes d is equal to 138.43 mm. Adopt d is equal to 150 mm with cover 50 mm, and d is equal to 200 mm, which means d is the thickness of the slab we have provided first. Area of steel required. For negative moment, mu is equal to 0.87 fy ast, d minus 42 u mx means moment. Then ast calculated is 1223.19 mm square. Using 16 mm dia bar, spacing required is equal to 201 into 1000 divided by this area. Then it comes 164.4 mm. Then we have this calculator. Place 16 mm dia bar at 150 mm center to center distance. Area of steel provided is equal to 1340, which is greater than 1223. Hence this is safe. Similarly for positive moment, AST is equal to 917.45. We have for positive, we have same 16 mm dia used. Then it has a design of dia 60 150 mm center to center. Then AST provided is 1340, which is more than 917, hence it is safe. And this is the diagram for this. Check for the deflection. Steel stress of the service, factor of safety is equal to 0.58 into fy 1223.19 divided by 1340 into 219.72 Newton per mm square. Percentage of steel provided is 0.67. Referring figure 4, IS 456 modification factor is 1.4. Then use this modification factor for minimum depth. Then it will 82. Allowable ratio is 36.4, and provided ratio is 1.15. Hence the section is safe in deflection. Check for shear. These are the formulas for checking shear. It become 183 kilonewton. Shear stress is equal to tau bd by tau by bd into is equal to 1.22 Newton per mm square. Now 100 AST bd is equal to this is from the IS 456. Shear reinforcement is required. Let provide the bent of bars. Area of the shear reinforcement for is equal to, it is calculated as 461.15 mm square. Then provide 12 mm of bar at 200 mm center to center distance, which is shown in the figure. Check for cracking. The steel provided is more than 0.12% of gross area. Spacing is less than 3D, hence it is safe in section. Then we have to design. First we have calculated the depth of the slab which is provided below the beam. Then after that we are calculating design of raft beams, which is FB2 and FB1 shown in the figure, which we will take uplift pressure 122.45 kilonewton per meter square, previously calculated. Load carried by the foundation or raft beams is shown in the figure. FB1 carries the load distributed on the two triangles. FB2 carries the load distributed on the triangle portion of the cantilever, which is shown in the figure. How to calculate FB1? Design of FB1. Area of loading 0.5 into 3 into 3. 3 is the center to center distance into 2 is equal to 9 meters square. then loading on the beam. After that we have to calculate moment supports, then moment at the mid span. These are formally taken from the IS 456. Depth of the beam, d minimum, we have assumed 400 mm. D minimum is equal, then calculated 670. Then we have adapted 720 mm and cover 30. Hence it is been, we have taken cover 30 mm. Overall depth D is equal to 750. On site we have taken 750 depth of the beam, and below the beam we have taken slab which we are calculated 200 mm. MU limited will be the greater than MU ultimate. Beam can be designed in singly reinforced layer. After for this formula, AST required is 22.17 mm square. Provide 8 bars of 20 mm dia. AST provided is 2512 mm square, which is greater than this. Hence it is safe. Design of FB1. After FB2, we are designing FE1. Check for shear. This formula from the table number 13 for SF coefficient for tau V 661.23 into 1000 divided by 300 into 800, which comes 4.132 Newton per mm square. For 100 AST by BD is equal to 0.872. Then this value comes tau C, and tau C max is taken. These are the same calculations for FB1. Structural details of FB1 and FB2. This is for the FB1 only. This is the slab which is taken below, and this is the beam, inverted beam. Then we have taken 200 distance of thickness of the slab and 750 for the beam. This is for the mid span, this is for the support. These are the some on-site examples of the, this is raft beam, this is the column, and below is slab. This is the beam junction. This is on-site some images. Reference I have taken for this IS 456 2000, IS 2950 part 1 1981, and from the Google. Thank you.
एक्सलेंट, बहुत अच्छा, बड़ा अच्छा कॉन्फिडेंस तुमने मेंटेन किया था जैसे, बहुत बढ़िया, बहुत सुंदर। नाउ यू कैन ऑफ योर स्क्रीन, यहाँ नीचे देखो स्टॉप। हाँ, नाउ गाइस बहुत ही सुंदर इन्होंने प्रेजेंट किया। नाउ दिव्यांशु अभी प्रेजेंट कर रहे हैं, आप लोग देखिएगा। और अभी आप लोग अगर एक थोड़ा बहुत भी पढ़ा होगा तो क्विक रिवीजन में आपको सब क्लियर हो जाएगा कितना अच्छा है। जयश्री ने बहुत अच्छा प्रेजेंट किया, पवन ने तो किया ही किया। दिव्यांशु आर देयर?
यस सर।
हाँ गाइस, दिव्यांशु के बाद कौन प्रेजेंट करना चाह रहा है? ड्रॉप द मैसेज प्लीज।
हेलो सर।
हाँ, वहाँ पर से स्क्रीन योर इंटायर स्क्रीन कर देना, योर इंटायर स्क्रीन।
हाँ सर करा, पर इसके बाद शेयर का ऑप्शन नहीं आ रहा।
उस पर क्लिक करना पड़ेगा, उस बॉक्स पे क्लिक करना पड़ेगा।
ओके
हाँ
ओके, यस सर। सर नाउ विजिबल?
यस, परफेक्ट।
Good evening everyone. Today we are here to see PDF on design of isolated RC footing. RC is reinforced concrete. First of all, there are some general notes like what is footing, what is a structure. So most of the structure built by us are reinforced concrete, and there are two parts of the structure. One is superstructure, which is above the ground level, and one is the structure which is below ground, known as substructure. Substructure where footing located. Foundation is that part of the structure which is in direct contact with the soil. So type of foundation also depend on the bearing capacity of the soil. The reinforced concrete structure consists of various structural components which act together to resist the applied loads and transfer them safely to the soil. So with the load coming on the structure, soil also plays the important role. In general, the loads applied on slabs in building are transferred to soil through beams, column, and footing. Footing are that part of the structure which are generally located below the ground level. They are also referred as foundation. Footing transfer the vertical loads, horizontal loads, and moment and other forces to the soil. So there are important purposes of foundations, that is footing. First, to transfer forces from superstructure to firm soil below, to distribute stresses evenly on foundation soil such that foundation soil neither fails nor experience excessive settlement. Because if soil settles or fail, our superstructure also fails, no matter how much of size column or beam or other elements are provided. If soil or substructure, that is foundation or foundation fails, or we may say footing fails, our superstructure may be collapsed. To develop an anchor for stability against overturning caused maybe due to wind or earthquake, to provide an even surface for a smooth construction of superstructure. Due to the loads and soil pressure, footing develops bending moment and shear force. So for calculations are made as per the guidelines suggested in IS 456-2000 to register internal forces. Code IS 456-2000 related to concrete, as we all know. So there are different types of foundations. First of all, these are based on the depth of foundation. That is shallow foundation and deep foundation. These two are based on depth of foundation, shallow and deep. So shallow foundation is provided where adequate SBC is available. SBC is soil bearing capacity, and if the ratio of DF upon V is less than 1, where DF is depth of footing and V is width of footing. If depth to width ratio is less than 1, we provide shallow foundation. In shallow foundation and in deep foundation, where DF by V is greater than or equals to 1. Further, there are different types of shallow foundations like isolate footing, combined footing, strap footing, bed or raft foundation, and wall footing. We further discuss each of them. Like for isolated column footing, so they are independent footing which are provided for each column. This is important. As also its name suggests, isolated, which means it is provided for each and every column. Where SBC is generally high, that is soil bearing capacity is high, column are far apart so that each independent footing can be provided there, and less on footing are less. And this is based on the column property, that is shape. And further, they are also classified as square, rectangle, or circular based on their shape, like this. After isolated footing, there is combined column footing, in which two or more columns are combinedly provide a single footing, and this is provided where SBC is generally less. SBC is more but less than where we provide isolated column footing. Columns are closely spaced, so this condition occurs when two columns are closely there, so that if we provide even isolated footing, the gap between two isolated footing is less, or either they merge. So to counter that, we provide combined footing for both the columns. And another reason is footing are heavily loaded, that is load coming of this superstructure is very high. So for the safety purpose, we provide combined footing there. Like this, these are two columns and a combined footing is provided for both the columns. Another is strap footing, an alternate way of providing combined footing located close to property line in the strap footing. Like strap footing is just like a way connecting two different footing, that is two isolated footing, through a strap, that is a beam. Like shown in this figure, we connected two different isolated footing with a strap. Another is strip footing. Strip footing is continuous footing provided under column or wall. Mainly strip footing is like if there are walls just above it, So we provide strip footing. A typical strip footing for a column is shown in below. Like these are columns and this is strap footing. So these are two different. Strip is different and strap is different. Don't be confused between both. Another one is mat footing, which is also known as raft footing. Mat foundation covers the whole plan area of the structure. The detailing is similar to two-way reinforced solid floor or flat slabs. We yesterday discussed flat slabs. It is combined footing that covers the entire area beneath a structure and supports all the wall and column. It is normally provided where soil pressure is low, that is soil bearing capacity is low, loads are very heavy, and spread footing cover area is greater than 50% of area. That means if we don't choose if we choose other type of footing like combined footing or isolated footing, and the area of that footing is greater than half the area of the uh, our total area, plinth area, or the design area, then we try to provide mat foundation. This is this figure also shows like there are multiple columns, and for all columns a single footing is provided. These all are shallow foundations. That means width to depth ratio is less than 1. Another type is deep foundation. Deep foundation is provided where the soil bearing capacity is low, as well as the adequate soil bearing capacity is available at a great large depth below, especially in southern region where black soil is there. So there we provide deep foundations. And there are further different types of deep foundation, like pile foundation, which is mostly used. Other one is pier foundation and well foundation. Well foundation is generally provided. It is also known as caisson foundation, and well foundation is provided uh, near the water bodies. So in that, a circular well is created, and then water is put out, and then uh, foundation is put there. So what is bearing capacity of soil? The safe bearing capacity of soil is a safe extra load soil can withstand without experiencing shear failure. The safe bearing capacity is considered unique at a particular site. That is, SBC is different for different site within a city, even within an area. It may vary or may not be vary. So if there is high-rise building where load coming is more, so generally it is safe to find out what is safe bearing capacity. For this, our soil sample collected from the site and geotechnical team provided us the SBC. So it is important for high-rise building. For residential building G+1, G+2, you may consider your area or your city SBC, but for high-rise building, SBC for the site is must. So according based on depends on SBC, size of footing, shape of footing, inclination of footing, inclination of ground, type of load, depth of footing decided. SBC alone is not sufficient for design. The allowable bearing capacity is taken as the smaller of the following two criteria, like limit state of shear failure criteria and limit state of settlement criteria. Based on ultimate capacity, that is shear failure criteria, the SBC is calculated as total load divided by the area of footing. That is usually the allowable bearing pressure varies in range of 100 kilonewton per meter square to 400 kilonewton per meter square. That is per meter square of soil we can easily apply load like between 100 kilonewton to 400 kilonewton. The area of footing should be so arrived that the pressure distribution below the footing should be less than the allowable bearing pressure of the soil. That is, for example, if the soil bearing capacity is 200 kilonewton per meter square, so our footing must be designed that it will transfer the load which is less than 200 kilonewton per meter square to the soil. If our design fail or footing may transfer more load than the capacity of the soil, then soil may be collapsed or settled, which ultimately results in the failure of a superstructure. Even for symmetrical loading, the pressure distributed below the footing may not be uniform. It means uh, if we provide symmetrical loading, which means if load is provided symmetrically or uniformly, it may not result in the footing may transfer it uniformly to the soil. It depends on the rigidity of the footing, soil type, and condition of soil. In case of cohesive soil and cohesionless soil, the pressure distribution varies in a non-linear way. However, while designing a footing, a linear variation of pressure distribution from one edge of the footing to the other edge assumed. Once the pressure distribution is known, the bending moment and shear force can be determined, and the footing can be designed for safely resist these forces. Uh, in this para, it clears that we consider that a pressure distribution is uniform, but in real, the pressure distribution is not symmetrical or uniform. It depends on the soil type and rigidity of the footing and condition of the soil. Like sometimes we see if there is heavy rain or flood-like situation occur, and soil below the surface structure drag down by water or drag away with water, then our superstructure collapse. So condition of soil also plays an important role. If condition of soil misbehave, then our superstructure may also fail. Then other point is design of isolated footing. This is my main topic, design of isolated column footing. Till now we discussed general things about footing or foundation. Now be specific on isolated column footing. So the objective of design is to determine area of footing. Here we are find out area of footing, thickness of footing, reinforcement details of footing that satisfy moment and shear consideration, check for bearing stress and development length. This is carried out considering the load of footing, SPC of soil. To determine these all things, like complete design of the isolated footing, we have to carried out loads of footing, soil bearing capacity, and grade of concrete and grade of steel. The method of design similar to design of beam and slab. That is, the designing method for footing is same as we design beam and slab. Since footing is buried, that is under soil, deflection control is not important. However, cracks width should be less than 0.3 mm. The steps followed in the design of footing are generally iterative. The important steps in the design of footings are: find the area of footing due to service load and assume a suitable thickness of footing. Identical critical section for flexural and shear. Find the bending moment and shear forces. Check the adequacy of the assumed thickness. Find reinforcement details. Check for development and bearing stress. A limit state of collapse is adopted in the design of isolated column footing, design of flexural, design of shear, design of bearing, and design for development length. The material used in RC footing are concrete and steel. The minimum grade of concrete to be used for footing.
दिव्यासु सॉरी टू इंटरप्ट, जस्ट डायरेक्ट आप टॉपिक पे जाइए, क्योंकि ना इस ये तो लगभग सबको इन्फॉर्म है। आपको अपना टॉपिक
Okay,
प्रेजेंट
sir.
करना है जो आपको न्यूमेरिकल जो आपने सॉल्व किया है।
Yes.
एंड गाइस नेक्स्ट कौन रेडी है? काइंडली
Yes, sir.
गाइस नेक्स्ट जो रेडी है ड्रॉप द मैसेज प्लीज।
So here are the specification for design of footing as per Indian Standard Code 456/2000. There are general footing shall be designed to sustain applied loads. So here we are in the designing phase. Like first of all, we have to decide thickness at the edge of footing. So in reinforced and plain concrete footing, the thickness at the edge shall not be less than 150 mm for footing on soil and not less than 300 mm above the top of piles. So for this, in case of plain concrete pedestal, the angle between the plane passing through the bottom edge, pedestal corresponding junction edge column with pedestal and horizontal plane. So this is the formula. Tan alpha must be less than 0.9 into under root of 100 Q0 divided by FCK plus 1. where Q naught is calculated maximum bearing pressure at the base of pedestal in Newton per mm square, and FCK is, as we all know, characteristic of concrete at 28 days. That is, for M20 grade, FCK at 28 days is 20, and for M25, FCK at 28 days is 25. Then for moments and forces, in case of footing on pile, computation for moment and shear may be based on the assumption that the reaction from any pile is concentrated at the center of the pile. For bending moment, the bending moment at any section shall be determined by passing through a section, a vertical plane, which extends completely across the footing, and computing the moment of force acting over the entire area of the footing on one side of the said plane. Other is shear and bond. So other important detail is tensile reinforcement. The total tensile reinforcement at any section shall provide a moment of resistance at least equal to the bending moment on the section, calculated in accordance with the 34.2.3 clause. Total tensile reinforcement shall be distributed across the corresponding resistance section as given below. So these details are all about how we provide the tensile reinforcement. Like in one-way reinforced footing, the reinforcement extending in such direction shall be distributed uniformly along the full width. In two-way square footing, reinforcement distributed uniformly across the full width of the footing. This is another formula. Next important thing is transfer of load at the base of column. So here is one numerical problem. For example, if we have to design an isolated footing for an RC column of size, that is minimum size 9 inch by 9 inch to 30 mm by 230 mm, which carries a vertical load of 500 kilonewton. The safe bearing capacity of soil, that is SBC, is 200 kN per meter square, and we have to use M20 and steel of grade 415. So first of all, we have to calculate the size of footing. For that, load on column is 600 kilonewton. Extra load 10% of load due to self weight of soil. So 10% of 660 kilonewton. So total load is 660. So required area of footing is P upon ABC, that is load upon soil bearing capacity. 660 divided by 200. So it is 3.3 meters square. Assuming a square footing, so side is equal to under root 3 over 3, that is 1.82 meter. That is, we have to provide a footing of size 1.85 meter by 1.85. So our one task is completed. Then net upward pressure in soil is that is pressure upon our size, which is 175.3 kN per meter square, and our safe bearing capacity for soil is 200 kN per meter square. So it's okay. Hence factor upward pressure on soil is this, and factor load and this. So this is simple design in which we calculate the size of footing according to load and check whether our soil bearing capacity and net upward pressure in soil is balanced or not. Again, next step is two-way shear. Assume an uniform overall thickness of footing is 450 mm. Assuming 12 mm diameter bar for main steel. So effective thickness of footing is 450 minus 50, which is cover, minus 12 and minus 6. So effective width is 382 mm, which is shown here. Here punching area of footing is A plus D square whole square, which is this side. Punching shear force, like in yesterday class, sir explained punching shear force, which is factor load minus force factored upward pressure into punching area of footing. So using this formula, we find out nominal shear stress in punching. So allowable stress, where tau c is 0.5 into FCK, which is 1.12. So allowable shear stress is 1.12 Newton per mm square, and our punching shear is this, which is less than allowable shear stress. So we can say the assumed thickness is sufficient to register punching shear force. So hence the assumed thickness of footing is 450 mm, which is sufficient. Size we already decided above, and the effective depth of the lower layer of reinforcement is this, and for upper reinforcement is this. Next step is design for flexure. The projection of footing beyond the column face is treated as a cantilever slab subjected to factor upward pressure of soil. That is, this area and this area is treated as cantilever. So factor upward pressure of soil is 263 kN per meter square. Projection of footing beyond the column face, that is this, which is 1.85 minus 810 mm. Hence bending moment at the critical section in the footing is mu is equal to pu L square upon 2. We put value here, and according to IS code, mu is equal to 0.87 F by ASTD 1 minus F by AST upon BD FCK. Here we take for every meter length of width of footing, we put all the values, and by using this equation or formula, we find out AST. Selecting the least and flexible value of AST, we have AST is 648.42. Other step is one-way shear. So for cantilever slab, total shear force along critical section, consider the entire width. So formula is Vu is equal to PUB minus D, 263 1.85 into 0.81 minus this. Again the nominal shear force is tau V is equal to Vu upon BD. We put all the values, and our nominal shear stress is there. So here from this all calculation, we find out that providing 12 mm diameter bar at 140 mm distance center to center. So here ASD provided is equal to 808, which is ASD more than the ASD required. So this is also okay. The next step is about to check for development length. Development length, sir, already we discussed. Sufficient development length should be available. Why we require development length? So sufficient development length should be available for the reinforcement from the critical section. Here the critical section considered for LD is that of flexure. So for 12 mm diameter of bar, development length is, for example, if we take 47 into dia, generally we take 50D, so it around 564 mm, and if we provide 60 mm side cover, so our LD is 750 mm, and which is also okay. Another is a check for bearing stress. So this is all about one complete example, and then this is other example.
लेकिन मुझे ऐसा लगता है दिव्यांशु आपने तैयारी नहीं किया था दोस्त, क्योंकि पीपीटी आपकी प्रॉपर नहीं थी। देखिए जो जयश्री का और इनका प्रेजेंटेशन था, देखा था आपने?
जी सर।
इन लोगों ने बहुत अच्छा प्रेजेंट किया, इसमें कोई वो नहीं है। आप फिर से, मैं चाहता हूँ आप प्रेजेंट करें एक बढ़िया सा न्यूमेरिकल लेके डिटेल में एक्सप्लेन करके, एक पीपीटी में सिर्फ एक न्यूमेरिकल को, ठीक है? लेकिन ऐसा कि लगे मजा आ जाए, ठीक है? एक्स्ट्रा प्रेजेंट कर दिए, कोई बात नहीं, प्रयास किया आपने, अच्छी बात है। बट जैसे अभी मुझे बहुत अच्छा लगा आज जयश्री का एंड पवन का बहुत ही सुंदर प्रेजेंटेशन था। तो गाइस हमें क्या करना है, मैंने आपको असाइनमेंट्स दे दिए हैं ग्रुप के अंदर, ठीक है? आप असाइनमेंट्स को चेक कर लेना। अभी हम लोग नेक्स्ट प्रेजेंटेशन करेंगे, वो करेंगे संडे को, ठीक है? क्या बोलते हैं, कल परसों मैं ट्रैवलिंग में रहूँगा, तो संडे को हम लोग का नेक्स्ट प्रेजेंटेशन रहेगा। उम्मीद करूँगा सब लोग अच्छे से रेडी करके रखेंगे, ठीक है? जैसा अभी इन लोगों ने किया, ऑलरेडी आपने देखा। और अच्छा देखो कितना, मतलब जो उन्होंने रिसर्च किया, देखो कितना बढ़िया रिसर्च किया और बहुत ही अच्छा प्रेजेंट किया और बड़ा कॉन्फिडेंस आया होगा, मुझे ऐसा लगता है। जयश्री आप फीडबैक देना, आपको अच्छा लगा जब आपने प्रेजेंट किया? तो जयश्री